So yeah, I'll mention a few open problems. These are reasonably tractable, so hopefully worth a try. And they came up in interactions with Muhammad, Amir, and Akshay at different points. Okay, so just to give some context for these problems, so non-black box techniques are pervasive in cryptography. Two examples which I really like are the first being FHE bootstrapping. So that crucially relies on this non-black box use of decryption inside encryption being used as input to the evaluation algorithm for the FHE to achieve full homomorphism. And additionally, it needs circular security along the way. And so this sort of a non-black box use is inherent in FHE bootstrapping, and we don't know a way around it. Okay? Another example is in going from functional encryption to indistinguishability obfuscation. Here, the decryption keys have encryption algorithms that are the functional decryption keys that are issued for a functional encryption scheme have encryption algorithms hardwired inside them. So that makes a non-black box use of the encryption algorithm in the decryption keys. Okay? So these are two sort of cool examples. But if you look at the I/O world, there are many, many applications, and many of them, or if not all of them, make some non-black box use of at least one-way functions or more. Okay? But this is not just about these high-tech techniques, as Muhammad called them yesterday, but also non-black box are fairly pervasive in the low-tech world. So where anytime you're just trying to prove that X is in some language, where the verification algorithm for checking that X is in the language makes oracle calls to some, say, even one-way function F, then if you're making use of such a zero-knowledge proof, you're already making a non-black box use of this function F. Okay? So for example, if you're using the NOR-Young CPA to CCA2 transformation, that's already non-black box. And if you're just trying to use NOR-Young, it's sort of not immediate, at least we don't know how to replace that use of NIZK in some black box way there. I mean, there are constructions that are black box, but just, if you directly wanted to give a proof, it's not clear how you could do that. Okay, so this raises the question of, how do we model these non-black box techniques? And the idea here is that if you have a primitive P1, P2, and you're using this, so P1, P, you could think of a primitive P, which comes with subroutines, like an encryption algorithm has keygen, enc, and dec. So I have a primitive P, a general primitive P, that comes with two algorithms, P1 and P2, and I'm trying to construct a different primitive X given this primitive P. Okay? Now consider this setting where this primitive is special in the sense that it takes in the input that's given to the, okay, so the input that is given when you're trying to execute this algorithm P2, one of the input that it receives is an arbitrary circuit C. So any person or any construction of a primitive X that uses P2 could execute this algorithm P2 on some input of circuit C. Okay? Now where the non-black box techniques come in is that if this circuit that I feed into P2 could have gates of P1 planted in it. Okay? So if I could plant P1, additionally I could also plant P2. So you could have gates of not just P1 but also P2, but in this case, and you could have different primitives which allow different levels of this planting, right? So you could have one primitive P that allows only P1 gates to be planted. Maybe completeness doesn't work if you plant P2 additionally. Or you could have a primitive that allows for both P1 and P2 to be planted. Okay? And this is not captured in the black box definition of Impagliazzo-Rudik and RTV. But this behavior is not common. In particular, the examples that I gave for FHE bootstrapping, going from FE to IO, and also proving in zero-knowledge a statement where the verification algorithm makes oracle calls, they all have this planting behavior. Okay? Okay, so this comes to just formalizing the model a bit further. The setting where we're planting one-way function gates in the circuit that is being fed to another primitive. So for example, if let's say you were trying to see if you can realize key agreement given one-way functions and zero-knowledge proofs that make non-black box uses of one-way function, then all you need to worry about is making oracle calls to one-way function and oracle calls to zero-knowledge with input circuits which could potentially have one-way function gates in it. But you're not right now thinking of having zero-knowledge gates, or if you're using a NIZK gates inside it. Okay, so just one-way function gate. And this was formalized by Berkowski et al., and they proved that this is not possible. You can't realize key agreement in this model. Okay? And more recently, Ashraf and Sergeyev showed that if you had one-way functions and indistinguishability obfuscation, where when you're using obfuscation, you can obfuscate circuits which also have now additionally one-way function gates in it, then this is not enough to realize collision-resistant hash functions. Okay? They made an argument here that including I/O gates here does not make a lot of sense, because if you have an I/O of I/O, you can unroll it and just make it one big I/O. So that was their argument, but it's not necessarily the case that in all settings this sort of layering may not be useful. Also in this case, this was sort of an intuitive argument. It's not a formal argument that you couldn't have more power by doing I/O of I/O. And finally, there's the monolithic model, which says that if any primitive takes a circuit C as input, then you can sort of allow for all kinds of gates of the oracles that you have to be planted in that circuit. Okay? So that's the models I'm going to talk about. So whenever I say oracle aided, I'm just talking about the one-way function gate being planted. Whenever I say monolithic, I want to sort of say all kinds of gates can be planted in all kinds of circuits that are fed to any oracle. So if you have multiple algorithms here that take arbitrary circuits as input, you could do all kinds of mixing and matching and so on. Okay? So what about garbling? So garbling is another powerful non-black box technique. And there, which we're going to model, and as Mohammed described yesterday, is one-way function gates, garble gates, and eval gates. He also talked about a reveal oracle, which I'm going to ignore for this, just describing these open problems that comes in the context of proving things. And what I would, if I'm trying to construct a primitive X in the presence of these oracles, where the garbling algorithm takes arbitrary circuit C as input, I could now plant in one-way function gates in this circuit when I feed it to the oracle garble. Okay? And so this would be in the oracle-aided circuit. If I wanted to talk about the monolithic model, then I could allow for one-way function gates, garble gates, as well as evaluation gates. So I could have maybe a garbled circuit takes another garbled circuit as input, evaluates it because it has the label somewhat hardwired in it, and somehow then computes something on the output and spits it out. Okay? So this is an extension of this model that one could think about. Okay. So the first problem, which is sort of the extension of what Mohammed was talking about, is doing public key encryption from one-way functions. So this problem does not need any motivation. So this is a very important problem. And the first question, which he answered yesterday, was can we do, which was in the negative, which is that this is impossible. We cannot do a public key encryption from one-way functions in the context of garbling in the oracle-aided model. So the only thing that's allowed is that you can plant one-way function gates in the circuit that you feed to the garbling algorithm. Okay? So what this does not tackle is the monolithic model, and that's one open problem that I think is interesting. So if the goal of constructing public key encryption from one-way function feels too far-fetched, then it's not unreasonable to then wonder if one could relax this one-way function assumption to the discrete, or work with a stronger assumption, the discrete log assumption, or an abstract version of it, a homomorphic one-way function, and try to see if you could construct public key encryption from the discrete log assumption. And that's also open. So we don't know public key encryption from the discrete log assumption. and it would be really worthwhile to rule it out if we can. And if there is hope of constructing it from these assumptions, it's likely that we would need non-black box techniques. So it's a worthwhile endeavor. There's also key agreement here. One point I want to make point out here is that the impossibility results do require care, and there are subtle aspects. So for example, if instead of if I didn't have garbling for circuits, but if instead it was garbling for tuning machines, then actually in that model it implies public key encryption. So I can use one-way functions and garbling for tuning machines to actually construct public key encryption, because garbling for tuning machines, again with the reveal function where there's just one-time execution, you could run the garbling on top of it again and again to get I/O, and then once you have I/O, you can use it with one-way functions to get public key encryption. So there, the edge between garbling and I/O in these models can be really subtle, and one needs to be careful in defining these oracles that we're not allowing for too much. So, okay, so this is the first problem I wanted to mention. The next one, which I think is perhaps, maybe if you think that this is, again, far-fetched, that public key encryption from one-way functions, maybe IBE from public key encryption is not as far-fetched. Yes?
So the previous slide, what I don't understand is, you can make garbling schemes from one-way functions in a black box.
Yes.
How is this different from just saying make PKE from one-way functions?
Yeah, so you can make garbling from one-way function in a black box way, but you can't make garbling from one-way function that computes that one-way function inside the belly in a black box way. Right? Make sense?
In 2 steps it becomes
Yeah. In 2 steps it becomes non-black box, in 1 step it is black box. Great question, yeah. So yeah, it can be, so this is sort of it makes the, and as I said, if this garbling was for tuning machines, if you don't do this one level thing, it's going to be impossible. But if you do this multi-level thing where a garbled circuit will actually spit out another garbled circuit, which will spit out another garbled circuit, then it'll suddenly become possible. Okay, so the next problem is IBE from public key encryption. And here I'm thinking of oracles that support public key encryption, so encryption, keygen, and decryption. And I have garbling and evaluation algorithms. And I want to construct identity-based encryption. And the only algorithm in the oracles that takes circuits as input is the garbling algorithm. So I could plant public key operations inside the circuit when I garble them. And it's possible that maybe I can realize identity-based encryption in this oracle-aided model. And so this has not been ruled out with any impossibility results so far. And the optimism stems from constructions from DDH factoring and so on that we've recently seen. And note that these constructions are also in the oracle-aided model in some sense. So they use DDH, but they don't do garbling, or the specific construction does not use garbling of garbling of garbling. It's just using DDH inside the garbled circuit. So the non-black box use here is limited. But if you're talking about impossibilities, it's interesting to look at the monolithic model and allow for all kinds of gates inside these circuits. Of course, there's some optimism, but there's some pessimism. If you can do IBE from any PKE, it will also solve, give you a generic, perhaps non-black box. Here in this case, construction of CCA, secure public key encryption scheme from CPA security, which we think is hard. So this is again, maybe it's a hard problem. So, but proving this impossible is an easier problem because it's a harder task to realize. Okay, so there are also extensions that one could think of, and for example, separating identity-based encryption from fuzzy IB. I think these are also interesting because I don't have the citation here, but we have a generic construction from identity-based encryption to hierarchical identity-based encryption, a non-black box one. So give me any identity-based encryption, and I'll use garbled circuits to construct a hierarchical identity-based encryption scheme. So is it possible to, and that, but we don't have such results for richer families of attribute-based encryption, say starting with fuzzy IB. So can we separate identity-based encryption from fuzzy IBE in the Oracle-aided model or the monolithic model? Yes.
Just a quick comment that, as far as I know, so in this slide, if you remove garbling, maybe it's just a good point that if you remove garbling, I think all 4 of these results already have some form of
Yes.
separation.
Yeah. So yes, exactly. So if you remove garbling from here, all the results are known. And then the we have no evidence that we could get a positive result in the.
CCH and CJ is not separated. There's some form of separation.
So that was on the previous slide, not this slide. Zvika, that was on the previous slide, not this slide. Okay. So yes, so that's. Huh? So this is just two things like in the Oracle-aided model or the monolithic model, and then this and your third and the fourth is the so on. Okay, so let's move on. So this is maybe from a positive standpoint, you might think that maybe these are unlikely problems. So that should suggest that the impossibility should be easier. The next open problem, or the next problem I want to talk about, is something where perhaps we are equally lost in both the positive and the negative side. So specifically, fully homomorphic encryption from leveled homomorphic encryption, as I mentioned on the first slide. So FHE seems to rely on circular security. The bootstrapping step relies on circular security. And there's been a lot of effort in trying to realize, or at least I think people have thought about, realizing fully homomorphic encryption from leveled homomorphic encryption without assuming circular security, or constructing circular security along the way so that you can construct it without specifically assuming circular security of the underlying scheme. And we haven't had progress, so it seems worthwhile to ask whether we can argue impossibility. And so what I want to describe here is a formal enough model where we could potentially give some kind of an impossibility result. So specifically, so this is the first step. I'll make it more precise in the next slide. So I want to say that, I want to realize a primitive FHE that in a world where it supports some level of homomorphism. So it's a leveled homomorphic encryption scheme. So it supports key setup, encryption and decryption, and evaluation algorithm. The evaluation algorithm takes arbitrary circuits as input. And you could plant all kinds of gates. So when I say PKE, it means setup, encrypt, and decrypt, all 3 of them. So you could plant all 3 gates as well as evaluation gates in the circuit and feed it to eval. Okay? And the question I want to ask is, can we rule out FHE from any leveled homomorphic encryption? But it's not very clear how are we going to ask this question, because when we are trying to this evaluation. So when we talk about leveled homomorphic encryption, it only supports circuits of a bounded depth, right? So, but I want to talk about this question independent of the depth of the circuits in the PKE, okay? So how I'm going to do is I'm going to frame this question as separate a depth k homomorphic encryption from depth k plus 1 homomorphic encryption. So if you have a homomorphic encryption scheme that allows circuits of depth k, you cannot use it to build the homomorphic encryption of circuits of depth k plus 1, even when you can make non-black box use of the underlying algorithms here. But I don't know the depth of them, so what I'm going to do is I'm going to go easy on you and say that anytime you use any gate from PKE or even the eval algorithm, that only costs 1. Okay? So I use cost 1 for that gate.
It's not easy on us, because then it makes the problem harder to rule out.
Okay, so it makes maybe the problem harder, so you can, at least it will give you a way of, if you want to be, make the problem easier, maybe you can say that, okay, if you use a decryption gate, it's only 1 depth larger than that, or you could tweak and make it easier then.
Why can't you use bootstrapping here? I don't know.
So if your underlying scheme public key encryption was circularly secure, then all I need to do is give an encryption of the secret key and hardwire that in the circuit. And what the evaluation basically does is does the decryption inside the belly. It's just a one depth gate.
So, why do you say there's a separation?
No. I'm saying that, okay, so if this underlying scheme was circularly secure, then you can do FHE.
From K to K plus 1, I don't need circular security. I only need circular security to do unbounded.
So you mean by growing the size of the thing? Yeah, of course. So take that, you will have to take that into account somehow. It's an open problem. I'm not solving the problem. So, yeah. So yes, so that's you'll have to take somehow that into account. But the key aspect here is that we have a model where if you assume circular security about the PKE scheme, it suddenly becomes possible. So the job is to come up with a setup where you can rule it out that circular security for such schemes is going to be broken or something like that.
For studies, just allow one call of the oracle.
Yeah, so as a starting point, you don't need to worry about making all calls here, but you could just start with a setting where only decryption calls are allowed. And again, I want to stress here is that even if you get this impossibility result, it does not mean that we won't have circular, fully homomorphic encryption schemes from LWE. It just says that you couldn't bootstrap. And that's still interesting because even if we have FHE from LWE, I mean full FHE from LWE, it's still worthwhile knowing whether if I gave you leveled homomorphic encryption, can I always bootstrap it further? So if you write this paper and someone rejects that, you can make this argument. Okay, so the next, any questions about this problem? I won't move on to the next open problem. Okay, so the next open problem is adaptive garbled circuits. So, in a garbled circuit, in the adaptive setting, we have an adversary, a challenger. The adversary gives the challenger circuit C. The challenger garbles this circuit C tilde, gives it back to the adversary. The adversary comes back with an input X. And the adaptivity is in the fact that X could depend on the garbled circuit that was just provided. And the challenger generates the garbled input for this and gives the garbled input back to the adversary. Okay? And we have two modes here. One is the honest mode, which corresponds to B equal to 0, where both the C tilde and X tilde are generated honestly. So our challenger is giving the adversary honestly generated garbled circuit and garbled input. And the other case is where the adversary is provided the simulated garbled circuit and a simulated garbled input. Yes? Yes, so that's, I haven't done it, it should be stateful, okay. Or, just give the same random coins to both of them. Okay, so at the end of the game, the adversary needs to guess the bit P, whether he got the real garbled circuit and garbled input or the simulated versions, okay. And the constraint here is that we want the online phase to be efficient. In particular, we need the X tilde to be much smaller than the size of the circuit. So that's the requirement for adaptive garbling. So there are 4 results that I know of here, or 4 ways of doing this that I know of course, except using indistinguishability obfuscation. So the first one is you could use the random oracle model and then the result follows right away. The second is you could get a result with an exponential loss in the security reduction, which basically goes from any selective to adaptive here very easily. There's a very ingenious solution here which makes the online cost grow either with the width of the circuit or the depth of the circuit. There are a bunch of papers that do that. And you can also do it in a non-black box way in Laconic OT. So I'll define Laconic OT later. I have another open problem, but there's another solution that does it. But this primitive itself is non-black box. It makes a non-black box use of that primitive. Okay, so the question I'm interested in here is can we rule out black box and non-black box constructions from one-way functions? So even though we have constructions in the random oracle model, it seems that if we want to get rid of the random oracle model, we have to do a non-black box use of public key assumptions to get a feasibility result. So ruling out black box constructions from one-way functions should hopefully be easy, but even that doesn't seem easy because of the random oracle result. Then, since we have we're even happy with non-black box constructions for more than public key assumptions, asking for impossibilities from one-way function, non-black box impossibility from one-way functions makes sense. And also just from public key encryption, both black box and non-black box impossibilities are interesting. Make sense? Okay. So that's the third open problem I wanted to mention. So you might imagine that, well, you have all these non-black box techniques. Should we forget about black box impossibility results? Well, no, right? Because there are various reasons why black box impossibilities are still meaningful. And the reason, even in a context where we might have a non-black box feasibility result, because they point to potential efficiency results, right? So if, let's say we have a non-black box construction, and it's interesting to improve on it to get a black box result, because it's typically going to be the case that the black box construction is going to be more efficient. And there are several examples where we have non-black box constructions and black box impossibility results. So in addition to the efficiency being an interesting aspect, the other, the talk by Lisa suggests that if you have a non-black box impossibility result and a black box impossibility, a non-black box feasibility positive result and a non-black box impossibility result, then that suggests that maybe it's worthwhile to look at more efficient non-black box techniques, right? So that's worthwhile to do. That wasn't on purpose. Okay, so there are many results here. So for example, one by Muhammad and Passe with non-interactive commitments from one-way functions, and we have two-round OT extension from the random oracle model, while we have this is impossible in the black box setting, while we have positive results in the non-black box setting. Same for IO. We have an impossibility result in the black box setting, while there's a feasibility result, as I mentioned on the first slide, if you make a non-black box use of functional encryption. So there are examples where we could prove lower bounds, black box lower bounds, even though there are non-black box feasibility results. So the next open problems I want to mention are in this context. So Laconic OT is a primitive which does the following. We have a sender and a receiver. The sender has, the receiver gets as input a large database D, so this D is large. Sender gets as input an index I, two strings M0, M1, and this index I is 1 to the size of the database. So it's one of the locations in this database D. Okay? So what the receiver does is he uses its database and the CRS to, it has to read its entire input, so it has to do work proportional to the size of this database D. It runs using the CRS and this database D, and produces a first message. Okay? It sends a first message to the sender, and what Laconic OT does is it requires that this first round message be small. Okay? So it's doing a lot of work, but the first round message that's sending needs to be small. And as it does a lot of work, it could prepare a pre-processed version of the database and so on, and keep it locally with itself. Okay? Then there's a second round message. What the sender does is that given the first round message, it's small, and the index I, M0 and M1, it generates the second round message. And I require that the amount of work that S does should be small, and that this second round message also be small. Okay? Finally, what the receiver does is that it learns M subscript D subscript I. Okay? So look at the ith bit of the database D. If it is 0, then the receiver learns M0. If the ith bit of the database is 1, then the receiver learns 1. And it's an OT, so it doesn't learn anything about the other message. Okay? So that's what a Laconic OT is. Okay? So there are 3 efficiency requirements. So let me state them again. The CRS needs to be small. I need the sender to be efficient. So note that because the sender is efficient, it implicitly requires that the first message be small. Because if the first message was large, the sender wouldn't be able to read it. And the third requirement is that the receiver in the second part of the execution, of course, it has to process the database, so that the first step, it cannot be efficient. But in the second step, when it has a pre-processed version of the database, so it has random access to that pre-processed database, and you could store anything. At that step, it must be efficient. Make sense? Okay. So this is a primitive that we know in a non-black box way from CDH factoring LWE. And if you were to relax any of these requirements, we can get a black box construction. Okay. Some of them are simple. One of them is an unpublished work by someone. So it's an unpublished work. I won't tell you which of them is. Let's stick with CDH. But I'm interested in efficient constructions. I want efficient realizations of Laconic OT. The closest that we come along with this is the LWE-based efficient construction, this Laconic function evaluation result. But the problem with that result is that the receiver work in the last step is still large. So it gets 1 and 2, but not 3.
So the CDH-based construction says information theoretic in the generic group model?
Yeah. So for example, that would be a black box construction, right? So that even from DDH, right, would be interesting.
You said that there is such a result?
No. There's no black box construction. Only non-black. From LWE, there's an efficient construction, the Laconic function evaluation one, but it suffers that 3 is not achieved. So 3 is not. The receiver in the second step is not efficient.
So if the CRS is not short, then you can do a black box from CDH, right?
If the CRS is not short, then you can do it black box from DDH, CDH, yeah, all of them, yeah. Okay. Yes. So that's this is interesting because as a primitive, it has many applications. Some of them, those applications use it in a non-black box way, so there'll be still a lot of work to get those applications, but it could be a good stepping stone. Also, there's this primitive called registration-based encryption, which I think it will be very cool if you can realize it in a black box way. And note that I'm not as concerned about the assumption here. Even if you can do it from in a black box way from pairing, that would be interesting, and that's something that we don't know. Okay. So, and it seems that it might even be impossible, and it would be interesting to rule that out. Yeah.
So two questions. First, this non-black box is what?
No. This is the primitive. The constructions of it.
The construction is non-black box.
Yeah.
What?
In CDH factoring LW. Yeah.
Because you say, what if it's black box under LWE? If you're using LWE, it's already
Yeah. So I'm saying, okay, so there are two levels of, the positive results can be framed in either black box or just, efficient construction. So when I talk about a positive result in the CDH world, I can say that, look, this is black box because I can do it. In the LWE world, because I can't say black box, I say, oh, well, this is efficient. In trying to prove impossibility, since I can't talk about, we don't have clean models for talking about LWE and giving impossibility results, I'm saying let's, not factoring. So, maybe it's good to start with CDH and just say, or DDH and say that, look, it's going to be impossible in the generic group model.
Can you capture factoring-based construction by hidden over group? Or maybe this is stronger even than generic group? So there's no generic model for factoring, or say quadratic pair is there is no generic model for factoring.
Well, okay, so so the negative result to hope for here is, or sort of the beginning first result, which probably also be the easiest to get, is prove that you can't do this in a black box way from DDH or the generic group model. Okay. Okay. So and even from pairing we don't know, and note that many of the applications from Laconic OT are known in a black box way from pairing. So for example, identity-based encryption. So there is hope, but it doesn't seem to work out. So ruling this out is interesting. Okay, so the last problem I want to talk about is that is in the context of CDH versus DDH. So these are two assumptions which are very closely, which are seemingly very closely related, but end up being very different when we're using them in applications. Particularly, we recently had this construction of malicious two-round OT from CDH. And we worked for some time on it. It took us some time to get this result, and it's very circuitous, and it uses garbled circuits. It's non-black box, and it seems like two-round OT seems to be one of that primitives where we can easily get it from DDH, but it seems to require a lot more work in getting it from CDH. So question to ask is, and we've tried getting a black box construction, and it doesn't seem feasible. So one might ask, can we rule out black box constructions from CDH? Again, you will have to, you can rule out black box constructions of two-round OT from CDH. So that would be interesting. Okay. A related problem here, which is also open, and will be perhaps a weaker goal because it implies you could use it to construct a two-round OT more easily, is showing impossibility of black box lossy Traber functions from CDH. So,
What's a generic model that distinguishes CDH from DDH?
so you will have to have a generic model that additionally provides an oracle that breaks all DDH style assumptions. Okay?
Any model that allows the pairing.
Yeah. So you basically have to do that. But it's you need to do it carefully because you could come up with DDH-looking assumptions where the exponent is in the denominator. So you need to look at polynomials, and it's a tricky exercise just to define that. But you could potentially do that, and once you do that, one could ask whether this could be ruled out. So note that for so hiding in this lower bound open problem is a upper bound as well, which is, so I said lossy Traber functions we don't know from CDH. So so two-round OT seems to be weaker than in the non-black box setting, weaker than lossy Traber functions in the sense that we can at least realize it in a non-black box way from CDH. But when it comes to lossy Traber functions, we can't even realize it so far from CDH. So this might be an easier impossibility, but maybe there is a positive result as well. So that's sneaking in a positive open problem as well. Okay, so that's all the problems I had. Any questions?